Okay, so now we'll see another kind of attack. So it is also a kind of denial of service attack, as we'll see eventually what happens. So it's called a TCP session hijacking attack. Okay, so let's use an example to go through this. So let us first look at, say you have a client and a server, and they go through the three-way handshake process, which I just explained earlier. So the client will send a SYN request message with a starting sequence number, which is say 3000, and the advertised window from the client's point of view, say 512 bytes. So the server will allocate some resources, some advertised window. Let us say it is 1024 bytes. This advertised window is the buffer space located by the server for that connection, and will send back a SYN plus ACK message. So let us say the starting sequence number from the server's point of view. So for whatever the packets the server will send, the sequence number up here will start from 8000. And so in the acknowledgement packet, in the TCP header, you have a sequence number field that will correspond to sequence number of the packet sent in one direction from whoever the sender is, and the acknowledgement number field will correspond to the acknowledgement for the other side, so for whatever the last packet that was received. And here I indicate, as I also said earlier, so you indicate in acknowledgement what is the sequence number of the next byte expected. So 3000 is the byte number of the SYN request message. So the server indicates that 3001 is the sequence number of the next byte expected from the client. And the client if it's a genuine client, so this genuine client is going to set up or complete the connection setup process by sending the third of the three packets, which is the ACK packet, by sending it accepts to all the advertised window size and all those stuff. And if at all I'm going to send any data, it's going to start with 8001 as its sequence number for the first byte, and then it also says, it will be 3001 for the client's data packets, and it also says the next byte expected from the server from the client's point of view is 8001. So the byte expected from the client is 3001 and the byte expected from the server is 8001. So that's the kind of agreement they come together and start exchanging the data packets. So far the session is going fine. So they set up the TCP session and they are now ready to exchange data packets. So it is the client who is going to send the data packets in the session. Of course, TCP sessions are duplex, so the data could be sent in both directions. Alright, so here the client sends 128 bytes of data starting with sequence number 3001. So the server gets all those that particular data packet, so all the 128 bytes are received. So the the server acknowledges for that, indicating that the next expected sequence number from the client is 3129. So when the client receives that, it implicitly means every byte before this has been received at the server. So that's how the acknowledgement is interpreted. And also, there's a sequence number field in the acknowledgement packet, so that will indicate what is the next byte sequence number that the client should expect to come from the server if at all the server is sending some data. So 8001 will be the starting sequence number of the data that the server will send if at all it is sending something. Okay, so far again everything is going fine. So the client now sends the next data packet, say it is 150 bytes large. So the starting sequence number is 3129, and that data packet makes it to the destination, the server, and the server acknowledges back with the next sequence number expected. So 3129 plus 150 is 3279. So that's the sequence number of the next byte expected from the client at the server side, and the server's own starting sequence number is still 8001. It has not sent any data. So now what happens is an attacker tries to hijack this session. In order to send this data packets acknowledged back and forth, the things that you need would be the IP address of the client, the port number at which the particular application process is running at the client, similarly the IP address of the server and the port number of the server. These four details are easy to get. It's all kind of public information. Now there are two more details that are needed. What are they? They are the sequence numbers of the next byte expected at the client side from the server and vice versa. So basically you need to know 3279 is the sequence number of the next byte expected at the server to come from the client. Similarly, 8001 is a sequence number of the next byte expected from the server at the client side. So in order to hijack this session, the attacker should be able to find out these two sequence numbers. Now that is another reason earlier when I did this TCP module, I mentioned you don't start the sequence numbers of TCP sessions from 0, because if you start from 0, you are making it more easier for an attacker to guess the current expected sequence number at each side. So you start from an arbitrary number. Okay, so the sequence numbers are 16 bits large, so you could go all the way up to 2 to the power 16. So you, and also using the timestamp field, you could enhance the sequence number space. So you start from an arbitrary sequence number and proceed from there. So that way you are making it more difficult for an attacker to guess the current expected sequence number at both sides. So given all these constraints, so how can the attacker still able to find out the sequence number? Now there are two ways you could do that, an attacker could do that. It is called a local session hijacking and blind session hijacking. So in local session hijacking, the attacker is in the same network, basically all the three machines, the client, server and the attacker are in the same network. So if the attacker is in the same network as the client and server, he could what is called capture all those packets on the channel, which is called sniffing. So he could run some packet sniffer program on the channel and capture all those packets and find out from those packets what's the next expected sequence number at each side. So that's why encryption, which we are going to see later, is suggested. Even if you want to communicate within the own network, you should encrypt your packet, the data portion and even the header portion if possible, and send the information so that it cannot be easily sniffed. Now if the attacker is not in the same network as the client and server, things become difficult for the attacker. So he has to do something called a blind session hijacking. So that is nothing but the attacker has to guess the possible sequence numbers, okay, and try to hijack the session. So that means in one go, as you see. So here we are going to assume the attacker has guessed the right sequence number, and we are going to see how the attacker is going to hijack the session. But unless if the attacker has not guessed the right sequence number, he cannot do like what we are going to see. He has to first guess the right sequence number, so he has to go through a trial and error process. Now that's where the firewalls come. So if the server is running in some network, and we are going to later see that as a solution next class, how the firewalls can detect this attack, but I'm telling the solution kind of right away. So if a firewall running at the network where the server is running sees that some packets come to the server, so the firewall should also keep track of what is the next expected sequence number for this TCP session at both sides. So if the firewall sees that some packets are coming to the server from the client with the sequence numbers that are not the expected ones, there are some random sequence numbers. So that is an indication to the firewall that someone is trying to hijack the session. So if the firewall sees some threshold number of such packets coming to the server, the firewall will not permit any more packets to enter the network and reach the server. It will drop all those packets. In that way, the genuine client is also kind of denied service. The firewall is trying to be proactive. So in one way, the attacker has kind of achieved the objective, because the client and server can no more communicate at that time. But at least the kind of the flooding of messages that we are going to see would have been prevented by then. Okay, so that is the kind of solution. So let us see how the attack is now conducted. Okay, so assume there is an attacker who has guessed the expected sequence numbers at both sides. So the attacker again does IP spoofing. So he'll send a data packet that will appear to come from the genuine client, and target to the server, and the sequence number of that bytes, the starting byte in that packet would be 3279, and that is the sequence number that the server expects in the next data packet to come from the client. So from the server's point of view, when it sees such a packet, it will think everything is fine with that packet because it appears to come from the intended client's IP address and port number, as well as this is the next expected sequence number. So it will just go ahead and process that packet. Now it could be that there could be some malicious, false, wrong information or something, even a virus attack or something as part of the code in this data packet, and the server could be affected because of that, or the attacker may just want to hijack the session, as we are going to see what's going to happen. So now the server will try to acknowledge. Of course, this is a data packet and this is a TCP session, so the server wants to acknowledge back to the client. So the server now sends an acknowledgement back to the client telling that this is the byte number for the next, so the sequence number of the next byte expected from the client. So starting from 3279, it has received 1000 bytes. So next expected sequence number should be 3279 plus 1000, so that is 4279. And it sends, it's also its own sequence number that will send in the next data packet, which is 8001. So the client, when it receives this acknowledgement packet, is going to be kind of confused. Okay, so it has not sent anything after 3278. So the client will try to kind of what's called resynchronize with the server by sending a dummy acknowledgement that the next expected sequence number from it should be 3279, right? So that's what it'll try to resynchronize with the server by sending such dummy acknowledgement packet, and also the expected sequence number from the server. So now what the attacker will do is he'll try to aggravate the situation. So he will send another 1000 bytes of data that appear to come from the client. So the starting sequence number is going to be that 4279 because that's what the server is going to expect to receive from the client. So again, the server is going to think everything is fine with the data packet and is going to send an acknowledgement with the next expected sequence number to be 4279 plus this 1000 bytes. So that's going to be 5279. And the client is going to be again confused and try to resynchronize by trying to send a dummy acknowledgement packet with 3279 as the expected sequence number. So things will go on like that. They'll try to resynchronize and the client server will say no, it is 5279 I am expecting from the client, but the client will say no, it is 3279. So they keep exchanging such dummy acknowledgement packets back and forth, and the attacker can aggravate the situation further by sending another 1000 bytes or whatever the amount of bytes of data and making the server to change its next expected sequence number. So what this is creating is an ACK storm for the client and server. They will keep sending these dummy acknowledgement messages to resynchronize. And when they exchange such ACK packets back and forth, that is going to flood the network at both sides and exhaust their bandwidth, as well as the server will be spending all its time trying to resynchronize with the client and not doing anything else usefully. So it's also a kind of denial of service attack because the server will be tied up in trying to resynchronize with the client, as well as the network at which the server is running, as well as the client is running, will be just flooded with these acknowledgement packets. So this is what is meant by TCP session hijacking. It's a very classical attack. Okay. So if you have any questions, you can ask. Let me save this as a video.